Op amps are really an integrated circuit, so they're really made of mini transistors, which we haven't talked about yet this quarter, but we will. We're sort of doing them out of order because this is a more practical application that we want to use in lab. Transistors aren't used as much anymore, but transistors are really important. It's important to understand sort of the basic physics of that it exists, but this is what we want to understand today is sort of op amps, right? And so you should just know underneath there's all these transistors, there's a lot of physics underneath there. But at the end of the day, we only have to worry about how does the op amp work. And so op amps are designed to have a very large gain that's designated by the symbol capital A naught, A0, a large input impedance. So the two inputs have a very large impedance, and the output has a very small impedance. And so you can see on this op amp, this is the symbol for the op amp. These are the important points. This plus represents the non-inverting input, usually designated V plus. The minus indicates the inverting input, indicated with a V minus. And then there's the output here at the end of this triangle. Now, these op amps require power, and so you have to power them up. And so typically on the over here, VCC, which we usually use is plus VS, and VEE, which is usually minus VS. And so the CC and EE have to do with the emitter collector of a transistor. For our purposes, it's not important what it is. The main point is it needs power, and that, in the end, how much power you give it could affect how the op amp runs. So if you don't have feedback, then the op amp acts as a comparator. So what's feedback? Feedback is a connection between the output connection, V out, and one of the inputs, V plus or V minus. So in the picture shown here, there is no feedback. There's no connection between the output and either of the inputs. And so we know it's going to act like a comparator. And in this state, V out is going to be given by the gain, A0, times the difference in voltage on the input. So A naught times V plus minus V minus. And so typically A naught's designed to be really large. It's on the order of 10 to the fifth. And so you could imagine if you had a 1 volt difference on the inputs, multiplied by 10 to the fifth, then you should have an output somewhere on the order of 10 to the fifth volts. If you stop and think about that, you'll say that's not really possible, and you're right. And so the limit is really going to be whatever your power supply, whatever the power you're supplying it with. Now there's some maximum power typically that you have to look up on a standard data sheet. But for us, we put about 15 volts on there. So plus VS is plus 15 volts, and minus VS will be minus 15 volts. And so that lets you operate between that minus 15 and plus 15 volts. So here's an example. So if you put 0 volts on the non-inverting input and plus 1 volt on the inverting input, then when you go to figure out what should be the output, you'd say it's the gain, 10 to the fifth, times the difference, V plus minus V minus in this case, which is 0 minus 1. And so the output should be minus 10 to the fifth volts. We know that's not really possible, and so what the actual is just going to be minus Vs. And so you can do the same thing, only we're going to put 0 on the non-inverting input, minus 1, then we'd expect the output to be 10 to the fifth volts. Well, that's not what we're going to get. We're going to get just the positive power supply, Vs. So whatever, you've hooked it up, 5, 10, 15 volts. So you can go on, and essentially it compares the voltage, and if V plus is bigger than V minus, you get the plus source voltage, and if it's less than, then you get the minus voltage. And so this sort of acts as a comparator. So this is typically not what op amps are used for, but nonetheless, this is their basic behavior when there's no feedback. So now let's look when we do have feedback. The output is connected to the input. So you can see in this picture there's some connection. There's a wire. That wire could contain any kind of impedance, a capacitor, an inductor, a resistor. Typically it's a resistor, but depending on your use, it could be anything. The main point is there's a connection, and this is what allows the op amp to change its output to match what's on the input. And so you get some dynamic properties for the op amp. Okay, so the main thing is there's feedback, and so this is sort of normally how we use it. So instead of using the large gain, 10 to the fifth, what we do is we wire it in this way so we get a smaller gain. Maybe we get a smaller gain somewhere, maybe 2, maybe 5. That's much more stable, and we can supply over a much wider range of frequency and input voltages. And so there's a few assumptions that go into the basic op amp. And so the ideal op amp assumptions with feedback are the following. 1, the open loop gain is infinite. Fine, we're not really operating at that, but we assume it's infinite. Number 2, the input impedance is infinite, so that means no current goes into those inputs V plus or V minus into the op amp. The output impedance is 0, so that means any current coming out of the output, there's no output impedance. So if we model that as a Thevenin's equivalent circuit, the Thevenin resistance would be 0. The op amp can change output instantaneously, right? This also means the slew rate's infinite. That means you can change. If you change 5 volts to 0 on the non-inverting input, then that'll change the output instantaneously. Now, that's not obviously the case, but that's the assumption. And both inputs have the same voltage. So if we're running it in this mode with feedback, then we're going to get feedback such that V plus and V minus are going to be the same. And then the performance doesn't depend on temperature or supply voltage variation. Okay, so those are the assumptions. What's this mean practically? And for all practical purposes for us in this class, we're going to assume we have ideal op amps. Essentially, the rules of operation with the feedback: 1, no current flows into the inputs of the op amp, and 2, V plus equals V minus. The feedback in the circuit is going to drive the voltage difference between the inputs to 0. So those are the 2 rules. That, along with Ohm's law and Kirchhoff's loop rule, will allow us to sort of say what's going to happen in any given situation. So let's look at a couple of examples. Before we do that, let's basically, when we are given these we have an op amp in a circuit, there's a basic cookbook for figuring out what's going on. So there's a lot of ways to do this. This is sort of what I think is the simplest way. First, we're going to check for the feedback resistor. If there's no feedback resistor, the op amp acts like a comparator, and we're going back to the previous slide on comparators, and that's going to determine what happens. Assuming there is a feedback resistor, we're going to assume no currents go into the inputs. We're going to determine V plus or V minus, whichever isn't connected to the feedback path. And we're going to assume V plus equals V minus. We're going to find the current in, right? And so I have it sort of drawn away from the op amp, but that could be going into this junction or away from this junction at the non-inverting input on this picture. Then we're going to find that current, which we can do using Ohm's law, and then we know at this junction right here, there's no currents going into the non-inverting input. We have current out through this 2 kilo ohm resistor, so that current must be coming through this feedback path, right? That's the feedback wire connecting V out to the non-inverting input. And so the current in must be equal to the feedback current, and then we can figure out the change in voltage of the feedback. That's going to be the change in voltage across the 4 kilo ohm resistor in this case, and then knowing the potential on the non-inverting input plus the change in voltage across this resistor will allow us to determine V out. Okay, so that's the basic operation. Let's look at an example. The first example has a name. It's called the op amp follower. So we're going to apply our sort of cookbook rules. We're going to say, hey, let's assume is there feedback? Yes, there's a feedback connection. The output is convected to the inverting input. So we're going to follow our cookbook. We assume no currents going into the inputs, V plus or V minus. So we put V in on the non-inverting input. There's no current, so there's just going to be a voltage. So we can say, hey, V plus is just going to be V in. We're making the assumption that the feedback is going to make V minus equal to V plus. So we know V minus is equal to V plus, which we know is equal to the input voltage. And then we can find V out. So V out, there's no resistor, so there's just connected by a wire. So the output voltage is really just going to be the voltage on the inverting input, and so that's going to be equal to the input voltage. So final end of the day, V out equals V in. We can figure out the gain. The gain is going to be V out over V in. In this case, that's going to be 1.